Hello? Hello, Belkut. Happy Monday to you, sir. Had a good weekend? I did have a good weekend. I was helping somebody move. So I picked up some heavy things, moved them through doorways, emptied out refrigerators, all that kind of stuff you do when you're moving things. What's up, Kate? Kate, I have a question for you, because I know you like Breath of the Wild. And so, I'm playing it through right now, right? And I discovered bomb jumping, or wind bomb jumping, or whatever. I mean, I didn't discover it, but it's new to me. And so I've been practicing that. And I think it's cool. I think it's cool how the in-game physics allow you to do lots of cool things. You've never actually done it? Come on, Kate. Good afternoon, Jack. Yeah, I'm enjoying Breath of the Wild. I just defeated that bird, Divine Beast, last night. I watched a speed run last year, and that was the first time I saw someone do the bomb jump thing, and it made me laugh so much. Yeah. Well, yeah, it's crazy. Like, or you can, like, chop down a tree, and as the tree is, like, tipping over, you can freeze it with the static thing. And then if you, like, whack the tree, it can go into orbit, but you can jump on the tree before it leaves. I haven't tried that yet. I'd love for you to do a class where you analyze the dynamics of Breath of the Wild. I know. Actually, you know, I want to try this because I know, because I have this capture card. I think it'd be easy to hook up the Switch. Hello, Nikta. Happy Monday to you. If I send you a couple papers about integrating social justice topics into engineering sciences, would you be interested? Yes. Yeah. I'd be interested. I've never seen a control system stream on Twitch. Nice. Hey. You came on a good day because we're gonna actually, I have this DC motor, and we spent a class period getting a model for this, and then we implemented a proportional controller first, and it doesn't work very well. So today we're going to modify the controller once more. So it'll be fun. There's some glitches too where you land on some monsters, and if you get the right angle, it literally shoots you up. And I've seen that too. I've seen that. I don't get it. Like, you jump off something like you're gonna shield surf, but then you land with the shield on the head of the boat of the Boko or something, and it launches you into space. Did you know Link is ambidextrous because in the original game, the sprite messed up and the shield was always on the north side. As a result, they said he always does that to ward off evil from the mountain. Ooh. Gartensurg says, what does the model include on the mechanical side? Friction, backlash, etc. Well, what we did, we used black box modeling. So we ran an experiment where we just introduced voltage in a square wave alternating, and then we fit that with a first order function because the behavior it's very close to first order. So it doesn't include like friction, backlash, all of that like first principles modeling. It's a purely yeah. Do you plan on holding extra office hours this week since the test is on Saturday? Let me tell you what I'm thinking. I'm thinking of during our Friday class session having a little bit of a review. That's what I'm thinking. So that'll kind of be like an extra office hour this week. Wait, what is this? That guy who sometimes stinks? Now this is too much. Because we have that guy who stinks. We have that guy who doesn't stink. And now you're telling me we have that guy who sometimes stinks. And it's just getting out of control. We need that guy who thinks. So we have the thinker and the stinker. Okay. Is there a printout for today? Yes, there is. But I uploaded it quite late. Dr. E, is your camera shaking or am I hallucinating? It might be because I think I was resting my arms on this desk and then I was like moving around and stuff. But I think it's stabilized. I'm gonna pay attention to it. What will be covered on the exam? Content through homework 3, basically. This is turning into Game of Thrones. Yeah, there's a lot of drama going on. Can I be that guy who stonks? No, you can't, Cross. John Cena, what's up? What is up? What made the control engineer go crazy? He got positive feedback? Oh my gosh. Are we really starting with the puns this early today? Can I turn down the music? Yeah, I'll turn down the music. Let's back it off a little, because we're going to get started here. You decide at birth a 2x2 grid with one axis of stink, not stink, and the other think, not think. Our digital controls channel is starting to develop some lore, some history. Hey, happy Monday, Pika. All right, let's get started here. So we are going to revisit this DC motor, and we are going to make an improved controller. But we're going to walk through conceptually how we get to this point. Happy Monday to all that do not stink. Okay. All right, where I'm going to the wrong screen. Okay, so that's where we're going today. And just a quick recap on what we did last time, because that was Friday, and it was a long time ago. But we're introducing some basic feedback notation. So we're going to refer to this block, this transfer function G, as the plant. And this is the system that we want to control. So in this case, this is the DC motor. D of Z is the controller. And what this amounts to, and you'll see this today, this amounts to one line of code on your microcontroller that tells us what voltage to provide to the DC motor. So there we go. The signal that comes out of the controller, we typically call it U. For the DC motor, this is a voltage. And the input to the controller is the error, E. And so here's where we have our feedback loop. So the error is the difference between the output, and this output for our DC motor is an angular velocity. It's in radians per second, in our case. And here is our reference angular velocity. So this is the desired angular velocity that we want to achieve. So the error is R minus Y. So the controller takes the error and it spits out a voltage which is provided to the plant. And the goal is, as with any control system, we want to closely follow the reference behavior. So last time, we derived a bunch of transfer functions. How do you measure the angular velocity? So there's a rotary encoder on here, and it's just picking up the angular position. And then I'm doing a real simple differentiation to approximate the angular velocity. So we're not using back EMF or anything like that. It's kind of a crude estimate of the angular velocity. So our plant transfer function G of Z, this is the Z transform of the output of your plant, which is angular velocity, over the input, which is the voltage. Our controller transfer function is the ratio of the Z transform of our control input to our error signal. Now, I put a star next to this guy. The open loop transfer function, actually, I don't think we talked too much about this, but it's the product of G and D. So if you take your controller transfer function and you multiply it with the transfer function for the plant, that's your open loop transfer function. Because I think last class I defined the open loop transfer function just as the plant, but that's not correct. John Cena says, do you teach grad level courses? Yes. Well, this is a mixture of senior level students and graduate students. I think we have mechanical engineers, electrical engineers, some computer science, mostly mechanical. Okay, the closed loop output error transfer function. So all of these transfer functions are just ratios of two quantities to each other, basically. So we have the error to the reference. That's the error transfer function. Yeah, represent electrical engineering, aerospace engineering. And it may E for life. All right, and then last but not least, the closed loop transfer function. And this is the most critical one. What is the difference between the closed loop and the open loop? Let me tell you the difference. So, open loop is, so let's go up here real quick. Open loop transfer function. So as the name implies, we're going to open up this feedback loop. It's going to be the ratio of y of z to r of z, but you're going to assume that you take a pair of scissors and you chop this, and there's no feedback going back. So the reference signal just goes through like this, and it never has a chance to come back. So no feedback. The closed loop transfer function is this same ratio, but we have this feedback loop intact. So open loop isn't even a loop. I know that might blow your mind, but that is the case. We've opened the loop, and so it's no longer really a loop, I guess. Okay, so that's just refreshing on this basic block diagram picture and some of the transfer functions that we're going to need to reference over and over again. Now, today our goal is to deal with steady state error. Maybe actually we should demonstrate the controller that we made last time so that you can see that it is it has some issues. It has some issues. Let's open this up. Open loop in general isn't a loop, only closed loops. All right, here is, so we're running this controller on Arduino, and I don't want to get bogged down too much in this, but this is a digital controller where we specify a time step, or rather, we've been calling this a sampling period. So 0.05 seconds elapse between measurements that we get in terms of angular velocity. So that means we're reading the angular velocity 20 times a second. And we're also sending commands to the motor 20 times a second. And we have this desired angular velocity, which is 1.5 times 2 pi radians per second. So this is in radians per second. So this is 1.5 revolutions per second. So that's what we want to do. And we're updating 20 times a second. We made a proportional controller. We derived this control gain. The goal of this control gain is to make the settling time around 1 second. And let me show you what we're doing with the reference here. Wait, where is it? Oh yeah, this is real basic. All this does is it sends an alternating square wave. So I'm just going to run, and this is our control input. We're saying U at time step K. U is the voltage that we're sending to the motor. So the voltage is some gain, which is minus 0.17, times the error. And here's the error. It's the difference between the reference angular velocity and this is our measured angular velocity. All right, let me upload this to our board. And then we're going to pop open the serial monitor. And you're going to be able to see that this guy is not doing very well. The blue line is the reference that we want to follow. And if you remember, well, the green line is what the motor's actually doing. And you see it spins in the wrong direction, and it spins way too fast. So it's a problem. And what we did to fix this is we saw how far off it was, and we made like a little feed forward term to try to adjust this, but we're going to get away from that today. Let's just see. I think this is what we did. We just augmented the reference a little bit. We said, okay, if it's going to go reverse of the reference, why don't we just reverse the reference in advance so that the controller follows something else and we trick it into doing the right thing, if that makes any sense. So we upload this. So this is all stuff that we did last time. Let's see if this works. So it calmed down. Okay. So now we at least got it kind of in phase. The green is following the blue. But there's still this steady state error, and there's kind of this asymmetrical behavior. So this was like a quick and dirty fix, and it doesn't really work that well. All right, so our goal today is to make this green line match the blue line in both directions. All right, unplugging that. We're coming back this way. So we can quantify this steady state error. And we derived the final value theorem to help us make this calculation. So look at this. This is saying the limit of the error as time marches forward is equal to this. Now this right here is just final value theorem. It connects some quantity in the real life domain, the error as time goes on, to this quantity in the z domain, which is kind of weird. But these two are equal to each other. And doing this math in the z domain is actually easier than doing it in the physical domain. So that's why we go to the z domain in the first place. But if you look at this, if you work out the math, okay, so we have this z minus 1 over z term. E of z, the error in the z domain, is equal to the combination of these two terms. Let me tell you why. This right here is one of the transfer functions that we derived up above. In fact, it's this one, number 4, the closed loop output error transfer function. So this is the ratio E of z over R of z, the closed loop output error transfer function. And then this, z over z minus 1, this is the z transform of a step reference, a unit step reference. So this is z transform of a step reference, which is the type of reference that we're sending to the DC motor right now. It's just a step up and a step down. So that's why we're using this function. So this is R of z in the case where you're using a step reference. So if you have E of z divided by R of z and you multiply it by R of z, you're just going to be left with E of z because the R of z's will cancel. So this combination of terms is E of z. And notice this. Z minus 1 over z cancels with z over z minus 1. So finding the limit of the error turns out to be as simple as just getting the limit as z approaches 1 of this one term that remained. Okay. So I want to introduce a little bit more terminology. So I covered this up, I realize. But I want to introduce the static position error constant. We call it K sub p. So this is the error when you apply a step reference to a control system. You can rewrite this as, by definition, so this triangle on top of the equal sign is meaning by definition, we're going to write this as 1 over 1 plus Kp. Is voltage U of z at the top had a printer jam and missed it? Yes. In this case, U of z is a voltage. Okay, so if you relate this term right here to this, you're going to see that we have defined the static position error constant to be, so I'm using this triangle again to be defined as, it's the limit as z approaches 1 of the product of g of z and d of z. And as we just defined up above, this product is called the open loop transfer function. Oops, just dropped my pen. Okay. So when we apply a step reference to our control system, this is what the error is going to be. The difference between where we want to go and where we actually are. So the question is, how do we make the steady state error go to 0 when we have a step reference? So the question I want to ask you is, if I want this error term to go to 0, what value do I need Kp to be? This is your first challenge for the day. Infinite. Yes. You want Kp to be as big as you possibly can. So the answer is make Kp equal infinity. And what is Kp? It's the limit as z approaches 1 of the product of g and d, which is your open loop transfer function. So I want this limit as z approaches 1 to be infinity. Or negative infinity. Don't even go there with me right now. Okay, now, let's think about this physically for a second. If I want to drive this quantity to infinity, g of z is our plant. It's the system that we're controlling. And you can't change this. Like this 6-volt DC motor, negative infinity is dead to us. That's right. Well, I need to go back and, because I remember we had an issue with negative infinity, and we were trying to figure out exactly what the role of negative infinity was in this controls thing, and I don't have a good answer yet. So that's why it's dead to us. I can't change this 6-volt DC motor. Yeah, you just made a pun. Let's stay positive. Okay. The controller, we can change this. Because in real life, this controller is just a line of code that we implement. So we can play around with that. We can't change this physical system G. This generally is what your open loop transfer function is going to look like. This is just like a generic mathematical placeholder for what that product could be. Can't stay positive, it'll piss off the controls. And is that a feedback pun? Okay. So, I'm going to rewrite this expression. If you factor out the roots of this polynomial on the top and this polynomial on the bottom, we talked about poles and zeros, right? You could write this polynomial as some constant c times z minus z1, z minus z2, and so this is the polynomial in the numerator factored into the zeros. Remember, the zeros are the values of z that make this transfer function go to 0. So if you can find a value of z that makes the numerator polynomial go to 0, then that's a 0 of the function. And then if we factor the denominator into its roots, we have the poles, because the poles are the values of z that make this transfer function go to infinity. So we're going to say we have m zeros n poles here. And if we take the limit as z approaches 1, if we want to have 0 steady state error, this limit needs to go to infinity. So let me ask you this. How is it possible for this limit to go to infinity? Can you think of a way that that could possibly happen? What are the conditions in the case where this ratio of polynomials would be infinite? Okay, add a pole. More poles than zeros. Poles go to 0. Okay, we're very close. This is going to be infinite if the denominator evaluates to 0. If the denominator evaluates to 0, that's guaranteed. If zi equals pi and c equals... No, you can't have... We're not going to make c infinite. And remember this, too. We're taking the limit as z goes to 1. So z is going to be evaluated at 1. Okay, so first thing... we want the denominator to evaluate to 0. Now consider this case. What if one of the open loop poles, which are pi, so I'll just, one of these, maybe it's number 1 or 2 or 3 or just any one of those in poles. If one of those open loop poles equals 1, so like what if P1 was equal to 1 or something? Then if I take the limit of this as z goes to 1, if I plug a 1 in there, I'm going to have 1 minus 1. I'm going to have a 0 here, and it's going to cancel out the denominator. We need some more pondering pugs. We'll put one right here. And this is kind of just like a loaf pug. Okay. So if one of those open loop poles is at 1, then the limit as z approaches 1 goes to infinity. Is that a seal? Might as well be. That's a loaf pug. Nightmare? That's not nightmare fuel. That's cute. That's adorable. Okay, so we're gonna put a statement over here with a star. here's a way to get this limit to go to infinity, which makes Kp equal to infinity, which makes your steady state error 0. Even the pug is overburdened during midterm week. I know. Okay, so if I wrote if again. If we have an open loop poll at z equals +1, we will have 0 steady state error for a step reference. Antonio says, end my suffering. Midterm week kills. Yeah. I hear you guys. I know midterm week is stressful. I know it's stressful. Hang in there. Hang in there. Okay. Let's talk about the DC motor then. 9 weeks left until PowerPoint graduation. Hey, we're over a third of the way through. This is the model we came up with for our DC motor. This is considering a sampling period of 0.05 seconds, 20 samples per second, all right? Now, the open loop transfer function, g of z times d of z, is going to be 1.796. So this is just z of z. This is just g of z. And then we're going to multiply this by our controller. Now, when we had a proportional controller, d of z was just equal to a control gain, k. All right? So, in order for our system to have 0 steady state error, this open loop transfer function needs to have a pole at z equals +1. So, a very easy way to do this, instead of just having d of z equal to k, why don't we add a pole at z equals +1? If we do this, we'll meet this condition up above, and we should have 0 steady state error. So what I'm proposing is, for now, we just do this. Open loop pole at z equals 1 should eliminate steady state error. Sorry, I forgot what the K does. So K, let me tell you what K was. When we did a proportional controller, that just means that d of z is equal to K. So the error comes in, and then the controller just multiplies the error by some proportionality constant. And the voltage is just going to be the gain times E. Not in space. Why are you allowed to just add the z minus 1? This is the beautiful thing about controls. Because, remember, the controller is just something that we're going to be implementing in a line of code. And I can make it whatever the heck I want it to be. I can make it, well, there's going to be limits you can see. But this is a beautiful thing. I know that I need an open loop poll at z equals 1. So I can just add one there to my controller. Because a controller is an abstract thing that we implement in code, and it can just be whatever. So to kind of get into your question, like how would I program this control law on a microcontroller? Because this might make it a little more sense. So d of z, the transfer function for my controller, is now equal to this. Well, what does the transfer function of the controller mean? It's the ratio of the z transform of the control input, which is a voltage, divided by the z transform of the error. Now, what I'm going to do is I'm going to multiply this out. So I'm going to multiply both sides by z minus 1. So u of z times z minus 1 is going to be equal to k times e of z. So I'm just taking this expression up above. I multiply both sides by z minus 1. And I also multiply by e. I can't relate to abstract thinking. Don't worry, don't worry. This is going to become concrete in a second. All right, let's expand this out. I promise this is going somewhere. So we're going to have z times u of z minus u of z is equal to k times e of z. Then what we're going to do is we're going to multiply this by z minus 1. And the reason I'm doing this is so that we can use the backward shifting theorem. So if I multiply this by z to the minus 1, it's going to be u of z minus z to the minus 1 u of z. And this is going to be equal to z to the minus 1. Wait, I'm going to write this differently. The gain times z to the minus 1 e of z. Now, we're going to apply backward shifting theorem to turn this into a difference equation. All right. So this, you could also think of this as the inverse z transform. But when I say that, it sounds spookier than it is. Because just watch what happens here. U of z is going to become u at time step k. Z to the minus 1 u of z by backward shifting theorem is just going to be u k minus 1. And then we're going to have this control gain. And then this is just going to become, by backward shifting theorem, e, the error at k minus 1. Now this is where it becomes concrete. To implement this control law on an Arduino, what it comes down to is in my line of code where I define what the control input is at some step k. It's going to be equal to whatever control input I used at the prior step plus some gain times the error from the prior step. I'm just going to put like a box around this. So it might take a little bit of time to wrap your head around, but what this development shows is that this difference equation is the same thing as implementing this transfer function controller. And all of this accounts for how the error was asymmetrical as well. It's a beautiful thing. It's a beautiful thing you're going to see. Okay, so but the work isn't done yet, like, because when I actually program this in the Arduino, I have to choose some value for that control gain. And that's where the real work comes in. Okay, so what I want to do. Okay. Let's state our goal here. This is our goal when choosing K. Choose K to place our closed loop poles in a favorable location. Now, after our first exam, we're going to use we're going to use the root locus method to place our closed loop poles anywhere we want. All right, and we're going to work on that. But for right now, with this structure of a controller, we're not going to have like complete control over where we place those poles. Let me just keep explaining this a little bit. The closed loop poles, this is going to be how our system behaves once we place the feedback loop on this. Or I guess when we implement this controller, that's the same thing as implementing the feedback loop. Flight dynamics student. For the exam, if we're comfortable doing all the homework problems, will we be all right? Yes. Will this right here be on this week's exam? No. The exam is going to be through homework 3. This is kind of going a step beyond that. Our closed loop transfer function. Let's go back here really quick. I'm just going to list what it is. The poles of this are called the... Wait, what does that say before location? Yeah, it says favorable. It's a little sloppy. So the poles of this, the values of z that make this transfer function go to infinity, those are the roots of the characteristic equation for the closed loop system. I know I'm using a lot of jargon here, but that's how the system is going to behave with this controller in place. A really nice way to visualize where the roots can be is using the root locus method. And right now I'm not going to get too much into details of this. In this class, we're just going to use built-in tools in Matlab to generate the root locus. Like I know when you take dynamic systems, we talk about the specific rules that you use and like the asymptotic approximations to sketch this thing by hand. We're not going to be doing that in this class. We're going to be using built-in tools to build the root locus. So what I want to show you, I want to show you how we make this. So let's go to Matlab really quick. Matlab. We're going to go over here. And we're just going to bang this out really quick. So we have this sampling period for our system. I'm going to make our transfer function for our plant. So in Matlab, you just use the tf command. And you put the numerator over here, followed by the denominator. And for digital control systems, you have this third argument, which specifies the sampling period that this transfer function corresponds to. For a continuous time system, you don't have to worry about this. And actually, this isn't super critical to include when you're doing the root locus, because it won't change that. But it's a good habit to include this term for what we're going to be doing in this class. So the numerator was just a scalar, 1.796, and the denominator was z minus 0.5134z. And then our transfer function d, first I'm going to do it this way, and then I'm going to fix something. So it's going to have numerator, denominator, and then our sampling period t. So the controller that we're trying out, it has the gain in the numerator. It's like k. And then the bottom is z minus 1. Z minus 1. Now, when you make the root locus in Matlab, you actually want to leave out this k, because the root locus command, what it does is it generates a plot that shows where the roots can be as you change k. So we actually don't want to specify k exactly. So I just put a 1 here instead of actually putting a specific gain. And what I like to do is I call this d with no k. That's just kind of my way of remembering that this is the controller that I'm using, but the gain hasn't been applied to it at all yet. And then what you do, you can make a figure, and then you can just use the rlocus command, and you want to put in here your open loop transfer function. Actually, maybe we'll do it this way. No, we'll do it like this. So the open loop transfer function is the product of G and D. But once again, we're ignoring that K value here. I like to make the axes equal. And heck, we'll even turn on the Z grid here. And so this just makes a root locus plot. So let's run this. It's thinking, okay, and then it generated this. And I'm going to blow this up a little bit. Actually, let's just go back to the surface because, wait, where'd you go? Wait, where's my OneNote? Good grief. Why don't we need to use the dot multiplication? I think I closed OneNote. Because you only need to use the dot multiplication when you're doing element-wise multiplication of vectors. And these aren't vectors, they're just transfer functions. So, hello? Okay, it's back. This is the root locus plot we made. Good grief, Charlie Brown! It is time to pack up. Okay, okay, it's 1:30. Let me take 5 more minutes. Okay. I went longer than I intended, but okay, what you're looking at here these are the possible root locations for our closed loop system. And notice there's two roots. So our DC motor was, it's a first order system, but when we added this new controller, the closed loop system is second order. So you actually see two roots. And when you use the root locus command, you see these X's here. Where you see those, this is where k equals 0. So if you were to set your control gain equal to 0, my closed loop poles would be here. And this would actually be a very poor choice because, well, this root here is just at the stability boundary, and our system will never actually settle. Because we know that roots out here, they never actually stabilize. So anyways, as you increase k, so it's only going to be positive values of k that this algorithm will use. As you increase k, these roots move. Like this one, well, like they move towards here, and then they reach this breakout point at some value of k. Actually, we could check that. If you click on here, right at that intersection, you probably can't see this, but the gain where that happens, which is, gain is the value of k, it happens at 0.033. So let's go back here. This is where k equals 0.033. Pretty interesting how the real component stays constant after the roots leave the real axis. It is interesting. Wait, why are k equals 0 there again? Well, they just are. Like, if you plug k equals 0, because what it's doing is it's generating this transfer function, and it's finding the values of z that make this go to infinity. So if you plug k equals 0 in for your controller, these two roots just happen to be where the roots are. All right, and then you're increasing k, and notice this. Once you increase k beyond a certain point, we leave the stability boundary. Where does that happen? And the controller is going to become unstable, and we won't test it out because I don't really want to break it. 0.274. So to have a stable system, I already know that the gain needs to be somewhere between 0 and 0.274. Okay, because we're running out of time, we're just going to pick a gain right now. What do you want to pick? What do you want to pick? Actually, let me show you something really quick. We're going to pick a gain, we're going to upload it really quick, and then I'm just going to show you, then we're going to be done. Let's keep it real. Something in between 0.033 and 0. Okay. 0.174. Let's do 0.0. I like 0.033. We're going to keep it real. And this is actually going to achieve the fastest possible settling time for our system. All right, let's go. We got to open up the Arduino code. Okay. So, okay, we got to comment this out. So watch this. This is going to be really straightforward. Zoom in a little bit more. This is what our controller was before. It was just a gain times the error. So I already had this like ready in advance. We're going to make this modification. So now the voltage that we send is, remember this is the difference equation we wrote out earlier. It's going to be equal to the previous voltage that we sent plus the gain times the error at the previous time. So we got to change this gain k to 0.033. Before we had this. So we're going to do that. Let's upload it. Okay. I need to... Oops. Okay, let's go to the plotter. Oh, it's beautiful. Notice, the steady state error is 0 on both sides, which is very interesting because we know that the behavior of this motor is kind of asymmetrical. So the red line is the voltage, and so what what would be interesting to investigate is on whichever side was a little bit weaker, you're going to notice that this controller automatically pumps a little more voltage to that side than it does to the other. So the voltage is the red line. Like, actually, I bet we could check right now if I look at this data in a different way. I think this second column is the voltage. So to one side it goes to 2.8, and the other side it goes to like 2.6. So the voltage is a little different. Let's go to the plotter again. Okay, now, like, we'll talk more about this conceptually, but I just wanted to show you mathematically first. Like, all we did is we took our controller, we knew that we needed an open loop pole at z equals 1. So we just defined a controller that actually does that. We made up a difference equation to make it a reality. And it turns out what's going on here is it's looks like it settles a little differently each time. I think it does. Wait, let's try a couple different gains. Now, shoot, we didn't have too much time to look at this, but if you remember this code that we made, what you can do is you can overlay the root locus on this. And if you do that, so maybe we'll play with this a little bit next time. But remember, these contours that we make, I'm going to unplug this for a second. These contours that we make are related to different behavior, like overshoot, settling time, rise time. So you can pick where you place your poles based on these contours. And so, like, earlier I was playing with this and I found one that had an overshoot of like 30% or something. Yeah, let's go back here. I can't remember which one it was. I think it was like this one. I think this has an overshoot of 30% and settles in 1 second. So we're going to upload this. And you'll just see that this has different behavior. So now, the roots of the closed loop system are complex. And if you have complex conjugate roots, You have oscillations. So this has 30% overshoot, but notice the steady state error is still 0 on both sides, because we preserved the property that there's an open loop pole at z equals 1. Man, there's so much to play with here and unpack. I wish we... So we'll come back to this on Wednesday, because there's like a little more we could do and play around with. And I think your first project for this course, you're going to be making your own controller for this motor. And what I'm going to do is I'm going to give you some performance constraints that you have to satisfy, and we'll have more sophisticated controllers that we can make, you'll see. And then we'll be able to test out the controllers that you make. You'll make better controllers than this. Okay, so that's it for today. We'll wrap it up here. Wednesday we'll come back to this. Yeah, undergrad students, you'll also be doing this. You'll be making a controller for this. You'll be using the root locus technique. Marx says, do you have time for homework questions? Sure I do. I also have office hours today. Don't forget that, guys. Homework is due on Wednesday. All right, see you, Antonio. I have office hours today from 4 to 5 on Discord. Is this still just a proportional controller? No, it's not. This is not a proportional controller. This is actually, if you were to break it down, I think it's a PI controller. We actually added an integrator to this. It's not PID. No, it's not PID. I mean, you can still ask me a question, Marks. That's okay. But I'll also be at office hours. Okay, we'll unplug this guy. Yeah, this is a lot of fun. This is why I love controls, because you can like connect theory with a real life thing, and you can make it work as you predict if you have a good model, and we have a decent model for this motor. Are we going to discuss lead lag networks? Yes. Yes, we will. Is this a university class? Yes. This is digital control systems at the University at Buffalo. Where does the integrator come into play? Is it the Z-1 that we added? Yes. Okay, till now, we were finding the discrete time roots using a specific settling time, but in the current homework, it's like a range of settling time. How should we approach that? Well, actually, in class, we did talk about achieving a range of settling times. Like, we spent a class period making a code that that fills in the range where the roots go. So if you go back to, like on UB Learns, I posted some links to the YouTube videos where we did that. But we did the code together. Yeah, this is fun, guys, because we're starting to get into the point of the course where, like I said, you have to build some of this knowledge first about discrete time roots and what they mean. And now we can start making controllers. The class itself is in the ME department, but there's a mix of us taking it. That's right. That's right. It's mostly mechanical and aerospace engineers. That guy who stinks. It's getting a bit more difficult, but interesting and practical. Really enjoying the class, Dr. E. Hey, thank you. I know we did a lot today. I know today's like drinking out of a fire hose. We're going to keep coming back and painting over this stuff over and over again, so it'll settle in gradually. So don't worry if you're watching this today and you're like, I have no clue what's going on. We'll keep reinforcing this over and over. Okay. Yeah, we have some electrical engineers. The EE gang. When I took Controls Lab 12 years ago, we did a PID controller for a water pump and a tank, but it was done in Simulink. Arduino IDE is so much more practical. GG. Hey, thank you. Yeah, now that there's these open source, really cheap microcontrollers, it's getting so much more accessible to do this stuff. So, yeah, I love Arduino. For the first project, are we going to be programming our controller in Arduino? No. So, I'm not going to focus in this class on the specifics of Arduino programming, even though I keep forgetting I want to share this code with you. The only thing that you're going to have to give me, if we go back here, where the heck are you? You're going to have to give me a difference equation like this. Hey, see you in office hours. That guy who sometimes stinks. But this is nice because you can derive this difference equation, and then it's very easy to just throw this in a line of code. So programming the controller itself is not too tricky. Is applying the backward theorem just to get that code we need for the Arduino IDE, or are there other uses to it? Yeah, I think the main purpose is to convert this transfer function into a difference equation that we can program on the Arduino. I think you said it very nicely. I think that's the primary purpose of backward shifting. It's the path that takes us back and forth between those kinds of representations. How's your semester going, Dr. E? It's going pretty well. Pretty crazy, just like you guys. I'm always trying to find a balance. Because it's easy in school or academia or whatever to just find yourself working all the time, and it's not sustainable. So I'm trying to always figure out a way to balance it a little bit more. I took a break this weekend, big mistake. Here's the thing, I don't know, like I can relate. So okay, for example, this Saturday I was helping a friend move. And they needed help, and this was a very good thing to do. And it was great. At the same time, I got home, early afternoon, and I was like, dude, I'm gonna crash. And I slept for like 2 hours. I took like a huge nap. And then I when I woke up from the nap, you know, when you wake up from a nap and you're just in a daze and like you, so there was no recovering. So Saturday was just boom. And like if you look at it from the perspective of, well, there's responsibilities that we all have related to school, and we're trying to not get behind, and so you could look at that as like, oh, I lost a Saturday. But at the same time, I think it was like a really great Saturday. And I think your mind gets like a little break, and because if you just keep going all the time, you burn out. My problem is I have nothing right now, but I know all my classes have upcoming unreleased. Yeah. That's the thing, too. Yeah, because you can't, as a student, you can't control when you're going to have a bunch of assignments and tests piled up. And so that's a tough thing about school. You're put in these situations where it's like, I just got to grind, and I'm not going to... Going through the first breakdown of the semester, so that's some progress maybe. Yeah, I think it's just good to know that school is very tough, and you're often in situations outside of your control where if your goal is to perform excellent and learn the best you can and get all your assignments done, it's going to put you in situations sometimes where it's just like, oh my God, there's so much I don't even know. And just knowing that it's not you, like it's just the way school is. And it's not going to, unfortunately, it's just a semester at a time. Like, you have to do it over and over again, but it's not like your life has to be that way ongoing, you know. My grandpa was an engineer, and he taught me a trick. For every 50 minutes you study or work, take a 10 or 15-minute break. It helps a lot. That sounds like excellent advice. Throwback to sophomore year when I was up till 4 a.m. during work every day for a week. Ugh. No thanks. Yeah, but I would say if you find yourself just totally crashing and burning, take a little break. And it doesn't hurt to like reach out to your professor or something. Sometimes there's nothing that can be done. But I mean, we are all human with finite capacity, and yeah, breaks are good mentally, but I always screw myself over because I have to play catch up. Yeah, it's a tough problem. It is a tough problem. Such is life, though. Yeah. Dr. E, I sent you a text on Discord. Did you get time to look at it? Oh, I remember what you're talking about. I saw it, and then I was like, I need to think a little bit more about this. I'll get back to you. I know what you're talking about. Hey, see you Wednesday, Belka. Hang in there, Pika. You're going to make it. All right, everybody. I'm going to move on with this day. Didn't mean to turn this into a therapy session. No, there's no reason to feel sorry. I love talking about this stuff. That's one of the things I really enjoy about what I do. I enjoy the technical stuff, but I also just enjoy interacting with you guys at what I know is a very stressful time in life. So I like to be there. All right. Adios, everybody.